to the CH1601 video series. The second set of Professor Smith's lectures focus on reactions relating to the carbonyl group and its reactivity. The carbonyl group has been briefly discussed in previous videos, but this video will recap the main ideas and slightly expand upon them. The carbonyl group, which looks like this, is a very important functional group. By changing this R group, we can have a range of different functional groups as shown here. It is important for you to understand the names and structures of these carbonyl-based functional groups. Initially, we will focus on aldehydes and ketones. Aldehydes must have at least one hydrogen attached to the carbonyl carbon. The other group can be hydrogen, a methyl group, a benzene group, or any carbon-based group. In a carbonyl group, the carbon and oxygen are both sp2 hybridized. The oxygen has two lone pairs in sp2 orbitals. There is a double bond, which hopefully you remember from previous videos, consists of a sigma bond and a pi bond. The sigma bond results from an overlap of two sp2 orbitals, while the pi bond results from an overlap of two pz orbitals. There are two main ideas regarding the carbonyl group, which are very important and will form the basis of the next few videos. The first is that a carbonyl group is susceptible to nucleophilic addition reactions. The second is that a hydrogen atom adjacent to the carbonyl group is acidic. Let's consider the first point. If we had an alkene with two carbon atoms, the pi molecular orbital diagram would look like this. Two p orbitals of equal energy overlap to form a bonding and anti-bonding pi orbital. In a carbonyl compound, the molecular orbital diagram looks more like this. Oxygen is more electronegative, so is lower in energy than carbon. This means the pi bonding molecular orbital is closer in energy to oxygen, and the pi star anti-bonding molecular orbital is closer in energy to carbon. In other words, the bonding orbital has the highest coefficient of electron density on oxygen, while the anti-bonding orbital has the highest coefficient of electron density on carbon. In any nucleophilic addition reaction, a pair of electrons can be added into the pi star anti-bonding orbital. Therefore, the nucleophile will always add to the carbon, not the oxygen. This concept is reinforced by electronegativity. The carbon is slightly positive, and the oxygen is slightly negative. The carbon center will be the electrophilic region where a nucleophile will add to. In the addition reaction, the nucleophile attacks carbon. Carbon can only have 4 bonds around the atom, so the carbon-oxygen pi bond breaks. A new sigma bond is formed between the nucleophile and the carbon. We can see there is a hybridization change from sp2, trigonal planar, to sp3, tetrahedral. If you can follow this basic mechanistic pathway, you will be able to understand all of the carbonyl reactions discussed in CH1601. In any generic carbonyl nucleophilic addition reaction, you must identify the electron-rich nucleophile, which adds to the electron-deficient electrophilic carbon atom of the carbonyl group, converting a sp2 reactant into an sp3 product. Now let's briefly look at the second point, the effect of the carbonyl group on acidity of an adjacent proton. Hopefully you will recall that we measure an acid strength by its equilibrium reaction with water. The more stable the conjugate base, pointed out here, the more likely an acid will donate a proton. The acid is therefore considered to be more acidic. In the acid equilibrium for this carbonyl compound, the conjugate base has a negative charge on the carbon atom, which can be delocalized into the carbonyl pi system as shown here. The negative charge is now on the more electronegative oxygen atom, which is far more favorable. Since our conjugate base is stabilized, the equilibrium will shift to the right-hand side, so the carbonyl compound is pretty acidic. To reiterate, This delocalization is possible because we have a set of sp2 hybridized atoms whose p orbitals are aligned in the same plane. This allows the movement of the pi bond and the negative charge within the system. How would the acidity of an aldehyde compare to a ketone or an ester? Take these three compounds and their conjugate bases. We actually observe that acidity decreases down this series. The OET group of the ester compound inductively withdraws electron density, but is also a mesomeric donor due to the presence of lone pairs. As mentioned in video 8, the mesomeric effect is more dominant. This donating group destabilizes the conjugate base by effectively pushing more electron density towards the negative charge. The equilibrium does not favor the right-hand side as much, therefore the acid is weaker. For the ketone compound, the alkyl group is inductively electron donating. Again, this destabilizes the conjugate base, but to less of an extent. The ketone is therefore more acidic than the ester, but still less acidic than the aldehyde. The final point I would like to mention in this video regarding the acidity of carbonyl compounds is if you have two carbonyl groups, such as in this compound, the acidity increases quite significantly. You can see the pKa of propanediol with two carbonyl groups is much lower than acetaldehyde with only one carbonyl group, meaning it is more acidic. How can we explain this? Consider their conjugate bases. The negative charge in propanediol's conjugate base can be delocalized in two directions. This makes it far more stable than the acetaldehyde conjugate base. So the equilibrium will be pushed further to the right-hand side. The Ka will be higher, so the pKa will be lower. It is important to understand the concepts covered in this introductory carbonyl video in order to master the upcoming topics. Try the quiz to test your understanding so far.